Here is an important concept. Sugars are also cyclic. Most common 5-carbon and 6-carbon sugars adopt a cyclic structure in solution, as shown here. D-glucose in its linear form looks like this. It's a Fischer projection. And when it gets cyclized, it either forms alpha D-glucose or beta D-glucose. I'll explain to you in a little bit as to how this forms. This occurs most commonly via the reaction of the alcohol on C5 with aldehydes, aldoses, or ketones, ketoses on the carbonyl carbon. So when I say carbon 5, so the hydroxy, this hydroxy attacks the carbonyl carbon, as shown here. And this results in a cyclic form, either a beta alpha D-glucose or a beta D-glucose. The cyclization results in hemiacetals or hemiketals. So what are hemiacetals and hemiketals? Okay, let's look at two different structures, aldehydes and ketones. The carbons, the carbonyl carbon in aldehyde and ketone is electrophilic. Remember, I told you about this. A carbonyl carbon, as shown here, it's polarized. So this is delta plus and this is usually delta minus because of electronegativity of the oxygen. Now, because of that, nucleophiles, like alcohol, can attack that carbonyl carbon. Alcohols can attack the carbonyl carbon. So, or alcohols, like this, can attack the carbonyl carbon. And this results in the formation of a hemiacetal if an alcohol attacks an aldehyde, or hemiketal if an alcohol attacks a ketone. And hemiacetal or hemiketal can then be converted to acetal if they further undergo attack by alcohols. So here is how cyclization of D-glucose happens. If you consider a linear or a Fischer projection of glucose, the hydroxy that is on carbon 5 attacks the carbonyl carbon, which is the aldehyde on carbon 1. Now, this structure is shown in a different way. So the linear form is represented in a different way in this structure, and what is shown here is the same, hydroxy from carbon 5, as you can see. Once this happens, there are two fates. The newly formed alcohol can either face down or it can face up. If it's up, it is called as beta D-glucopyranose, and if it is down, it is called as alpha D-glucopyranose. And this animation that is running here explains how this happens. Pentoses and hexoses readily undergo intramolecular cyclization, as shown here. The former carbonyl carbon, which is the aldehyde, the first carbon, becomes a new chiral center, as you can see. If the hydroxy is down, it's alpha D-glucopyranose, and if it's up, it's beta D. And this new chiral center is called as the anomeric carbon. This carbon 1 in the cyclic structure is called as the anomeric carbon. Another word for you to remember. the former carbonyl carbon becomes a hydroxyl group. The position of this group determines if the anomer is alpha or beta. Now, if the anomeric hydroxy group is on the opposite side of the ring as CH2OH moiety, the configuration is alpha. This is functionally equivalent to anomeric hydroxy cis to the reacting OH group, best visualized in the Fischer projection. So the easiest way to remember is this. If you now consider the stereochemistry of the CH2OH, it's up. If OH is on the opposite side or the trans side, then it's alpha D glucopyranose. If the hydroxyl group, this hydroxyl, is on the same side or the cis side, then the configuration is beta. That's all it matters. You may have realized by now that cyclization of sugar monomers introduces another source of variability. Monosaccharides that differ only in the stereochemistry around anomeric carbon, as hemiacetals or hemiketals, are called as anomers. Remember, sugars are hemiacetals and hemiketals. They are not acetals and ketals. They are hemiacetals and hemiketals, and when they differ in their arrangement on anomeric carbons, they are called anomers. Specifically, anomers will have either alpha or beta in their name.